Hello everybody, welcome back to another lecture video. In this lecture video, we're going to be covering constitutive laws, which is going to be such an important thing, especially once we start talking about the finite element method and we start saying, all right, well, if I have this much stress, how much strain do I have? Or vice versa, if I have this much strain, how much stress do I have? So the relationship between stress and strain, that's what we call a constitutive law, and that's what we're going to be discussing in this lecture. So again, just a little recap. Constitutive law, basically saying a stress-strain relationship. So in previous lectures, we've talked a lot about the stress tensor, we've talked a lot about the strain tensor, but thus far they've been independent for each other. When we talked about the stress tensor, we talked solely about the stress tensor and nothing else. And the same goes for the strain tensor. When we talked about the strain tensor, we said, all right, nice strain tensor here, but we didn't talk about stress. They were independent of each other. So now the question becomes, can we figure out a nice relationship for the two? So again, we have our stress tensor, we have our strain tensor, and the question really becomes, if I know the stress tensor, can I find my strain tensor, or vice versa? If I know my strain tensor, can I find my stress tensor? So what exactly are we going to have to do to convert from stress to strain, or vice versa, strain to stress? The problem is if we look at these, the strain tensor and the stress tensor are both matrices of M3, or second order tensors. Therefore, a relationship between the two, or a linear map from M3 to M3, that's going to be a fourth order tensor, which is going to be quite complex, as we're going to see. So for instance, let's say that I wanted the stress component sigma 1, 1. Well, a relationship for it, if I'm trying to relate it to the strain tensor, it'd be some constant times epsilon 1, 1, plus some constant times epsilon 2, 2, times some constant times epsilon 3, 3, etc., etc., etc. So if I'm trying to find the stress component sigma 1, 1, there's going to be 9 constants all multiplied by the 9 different values of strain that we have. Because keep in mind, our strain tensor is 3 by 3, so therefore we have 9 different values of strain. If we were to represent this in matrix form, as we can see, it becomes quite a mess. We have basically a 9 by 1 vector, another 9 by 1 vector representing the stresses and the strains. Therefore, a linear map or a matrix between them is going to be 9 by 9, which is going to be a lot of coefficients. So if we were to look at this and take a step back, the first thing that we see is, well, if we're converting from, if we know our strains and we multiply it by a map and it gives us stresses, well, therefore, the units of this C matrix will be MPa, or stress. So basically the C matrix here, the matrix that converts stresses to strains in this order, that is going to be called our stiffness matrix. So what we're going to do is we're going to try and figure out what these coefficients are in this stiffness matrix. Now again, a stiffness matrix C is something that's multiplied by the strain vector to give us stresses. If we multiply a matrix by the stress vector to get strains, as you guys will see a little bit later, it's actually called a different one. So this C matrix, stiffness matrix, this one's multiplied by the strains to give us stresses. And we'll talk again more about that a little bit later. Now, if we're trying to determine these coefficients, let's just take a step back and look and say, well, we actually have 81 coefficients right now. The matrix is 9 by 9, so therefore we have 81 coefficients. Now, you guys may be saying, spoiler alert, we're not going to need all 81 coefficients. There's going to be a lot of reductions. So let's go through some of the reductions. The first one is the symmetry of the stress and the strain tensors. So as we talked about them before, both the stress and the strain tensors are symmetric. For sigma, if we had sigma ij, well, that's equal to sigma ji. And the same thing for epsilon. If I have epsilon kl, that's going to be the same as epsilon lk. So if you guys remember in the previous slide, we had our stresses and strains as 9 different components. However, since we have symmetry, we know that we don't actually have 9 components, but we only have 6. Now this plays an influence in our stiffness matrix C. Because if we look at the first two indexes of our C matrix, we had ij. And because our stress tensor is symmetric, therefore that's the same as ji. And the same thing goes for our strain tensor. We know that the last two indices, kl, well, those are going to be the same as lk. So if we were to represent this now in matrix form, we have our stress and our strain as only 6 component vectors. Therefore, the matrix between them is now 6 by 6, which basically means that we have 36 constants, which is great because we took the 81 constants, we said we don't need this many, and we kind of narrowed our way down to 36. Now, this kind of not really part of the theory, but just a little tip for you guys because professors love to do this. As we're going to see in the next slide, so we haven't seen it yet, but as we'll see in the next slide, this C matrix, the stiffness matrix, is actually symmetric. All right, it's going to be symmetric. Now, professors are always going to ask, why is this one symmetric? And everyone will say, oh, well, if the stress and the strain are symmetric, therefore C must be symmetric. And that is the wrong answer, so please do not fall for this trap. Again, we're going to see that C is symmetric, but it is not because the stress and the strain are symmetric. The stress and the strain being symmetric is good because it helps us narrow down the constants, but it does not prove the symmetry of the stiffness matrix. So the question you guys might be asking is, all right, Clayton, how do we prove the symmetry of that stiffness matrix? Well, that actually comes from preservation of energy. So further reductions can be made if the material is elastic. So in this course, and many of the courses that you guys will see, we're going to assume that the material is elastic or that it preserves energy. This means that energy is stored when the material is loaded and then fully recoverable when it is unloaded. So if I have a piece of metal and I stretch it uniaxially in tension, it's going to have some potential energy. And when I unload it, it's going to go back to the original position and all that energy will be recovered. Now, what does this look like graphically? Well, if we had a stress strain curve of metal, the potential energy is the area under this curve. So that U with the bar up top, that is my strain energy function. Therefore, when I load this material uniaxially, we can see that we have a curve, and the area under that is actually going to be defined as my strain energy. Now, when I unload this, it's going to follow the same path back. Therefore, the area under the curve will turn into 0, and that's what we mean by the energy is also fully recoverable. All right. But now again, let's look in this. Look at the sense on how does this prove the symmetry. Well, if we see that the area is, the strain energy is simply the area under the curve, and we have a rectangle, well, we know that this strain energy is simply going to be 1/2 of sigma times epsilon. And the only reason why I'm not doing indices right now is we're looking at the uniaxial case, and this will just help make it a little bit more simple from now. So if we look at this and we say, oh, hold on a second, well, that sigma term in there, we know that if we want sigma, all we need to do is take our stiffness matrix C and multiply that by epsilon. So what I'm going to do is instead of sigma, I'm going to replace that with C times epsilon. Therefore, I end up with the equation of 1/2 of C multiplied by epsilon squared. Now I'm going to do something a little bit funny. Again, it's not going to make sense what I'm doing right now, but it will in the end. So now I'm going to take that strain energy function U, and I'm going to take the partial derivative, or in this case the total derivative, since we only have that one variable. We're going to take it with respect to epsilon. So all I'm doing is I'm taking the derivative of that strain energy function with respect to epsilon. Since we have epsilon squared, all we do is bring down the 2, and it turns into 2 times 1/2, which is just simply 1, times C times. So the partial derivative of U with respect to epsilon is just going to be C times epsilon. And we say, hold on one second, C times epsilon? Well, that's actually equal just to the stress component. Nice and easy. So from there, we can go one step further and say, all right, well, that means that my sigma ij is actually equal to the partial derivative of this strain energy function with respect to epsilon ij. Now again, you guys are going to say, what is that, Clayton? Well, don't worry. We're getting to why that's going to be important. The reason why it's important is because we're going to use this relationship to actually prove the symmetry of the stiffness matrix. How do we do that? Well, we realize that we have a linear relationship. Therefore, that stiffness matrix C, or the componentCijkl, that's going to be the partial derivative of sigma ij with respect to epsilon kl. Now, why is this important? Well, from above there, we actually derived what epsilon ij is equal to. It's equal to the partial derivative of the strain energy with respect to epsilon ij. Therefore, I'm going to substitute that bad boy in there. And we get thatCijkl is actually equal to the second derivative of the strain energy with respect to epsilon ij, and then with respect to epsilon kl. Now, here's where the magic happens. For those of you math nerds out there, we know that it actually doesn't matter what order we take the derivative in. If we take it with respect to ij first, and then take it with respect to kl, well, that's actually going to be the same as taking it with respect to kl, and then ij. Therefore, this second derivative at the bottom, we can actually rearrange the terms. So instead of having ij first and then kl second, I put kl first and ij second, which means that this is actually equal to c kl ij. What does this mean? Well, it means that Cijkl is actually equal to CKL ij. Therefore, our stiffness matrix C is symmetric, which is great. Because if we were to now look at the components, we went from 6 by 6, which is 36 components, down to 21. Notice that we're still having a 6 by 6 matrix C, but since it is symmetric, we know a lot of the diagonal component or off-diagonal components just because of that symmetry. Now, when you guys are given the question, why is the stiffness matrix symmetric? Remember, it's a result of that elasticity. It is not a result of the symmetry of the stress tensor or the strain tensor. It's because of this preservation of energy due to elasticity. Now we look at this and we say, all right, we got 21 components, but that still sucks. No one wants to deal with 21 components. What other reductions can we make? Well, as you guys will see, there's going to be one more reduction, and it has to be, or it is a result of planes of material symmetry. Now you guys may be saying, well, what is that? Well, basically a material behaves in an identical manner in different basis sets, and we're going to look at 3 types of materials in order of complexity. So the first one, which is going to be the most complex, would be orthotropic materials, and we get a little bit easier with transversely isotropic materials, and finally we're going to finish it off with the most common one, the one you guys probably know the best, and that is isotropic materials. As you guys will see for isotropic materials, we take those 21 unknown coefficients and we basically simplify it down to just 2. All right, so isn't that great? We can take a 6 by 6 matrix and fully define it using only 2 parameters. I know it sounds great to me, so let's get into it. The first thing that I want to talk about is just what is a plane of symmetry, because again, we said that we're making all these reductions due to planes of symmetry, but it's kind of hard to figure out what a plane of symmetry is. So basically what it is if the constitutive law, remember that C matrix, governing a material remains the same after a reflection about a plane, that plane is referred to as a plane of symmetry. So let's say that I had a material here in 2 dimensions, so it's defined by E1 and E2, and I have my relationship as follows, where sigma ij is equal to Cijkl times epsilon L. Now, let's say that this green plane here, which is vertical throughout this little square, is a plane of symmetry. What this means is if I were to reflect that E1 axis about this plane of symmetry, so if we look at the transformation after, the E1 prime now points in the opposite direction, and this is governed by this specific material behavior. This is a plane of symmetry if Cijkl is equal to C prime ijkl. So basically after that reflection about the plane of symmetry, that C matrix does not change. So we say that if Cijkl, which is the constitutive law in the original basis set, so E1 and E2, is the same as C prime ijkl, which is the constitutive law in the reflective basis set, we say that that green plane there is a plane of symmetry. Why are these so great? Well, it's going to drastically reduce the number of coefficients that we want to figure out. So the first one, which I said is the most complex, is an orthotropic linear elastic material. Now, an orthotropic material has 3 planes of symmetry with unit normal of the planes aligned with the basis vectors. What does this mean? Well, it basically means that the behavior of this material is different in each of the 3 basis directions. For instance, if I were to take my material and stretch it along E1, that would be a different response than if I were to stretch it along E2, and that would be a different response than if I were to stretch it along E3. Therefore, the 3 directions, it actually matters. The material behavior is going to be different based on which direction you pick. But because of that, the constitutive law must be the same after the following reflections, and the reflections being those 3 planes of symmetry. Therefore, this is saying, well, if the E1 plane is the plane of symmetry, or E1, E2 plane, then I can have reflection, and then the second reflection, and then the third reflection. So these have to do with the 3 planes of symmetry. Now, this is where things kind of become a little bit of a problem when we're trying to think of just matrices rather than tensors. So remember when I say the stress tensor and the strain tensor, I said for your purposes, we can interchange those with matrices for this course. But this becomes a problem when we start to realize, well, I'm trying to transform a 6 by 6 matrix with a 3 by 3 matrix. It makes no sense. So what we're actually going to have to do is realize that this C, this stiffness matrix, it's actually a 4th order tensor. Now, a 4th order tensor can be transformed by these 2nd order tensors using the following relationship, where C prime ijkl is equal to qmi, qnj, qrk, qsl, and CMNRS. There's an implied summation over the indexes using Einstein notation, but I left it out here because the proof of this is really outside the scope of this course. And I just want to emphasize that this is the way it is because C is actually a fourth order tensor. It's not really just a 6x6 matrix. All right, so again, we're not going to do the derivation of this, but basically what we do is we analyze each one of the components, and this results in 12 of the 21 components actually being equal to 0. So if we look here, there's now a lot of zeros just by analyzing the equation above and utilizing those planes of symmetry. Now, what's something special that we see is actually called shear decoupling. So if we were to look at the two corners of this matrix here, we have a bunch of zeros basically. What do these zeros mean? Well, let's look at the normal stress sigma 1, 1. We see that it's going to be a function of epsilon 1, 1, which is a normal strain, epsilon 2, 2, which again is a normal strain, and epsilon 3, 3, which again is a normal strain. Now, when it comes to the shear strains, all of those coefficients are now 0. Therefore, normal stresses in this case are only going to be a function of normal strains. Shear strains play no impact on normal stresses and vice versa. If I was looking for normal strains, then the shear stresses play no impact if we're looking at those specific ones. The other one we can see is we have a bunch of zeros in the shear components. What does this mean? Well, it basically means that sigma 1, 2, the shear stress 1, 2, is actually directly proportional to the shear stress epsilon 1, 2. Now, notice that 1, 2 is only proportionate to 1, 2. We don't see that we have we don't have sigma 1, 2 equal to something times epsilon 1, 3. It's only 1, 2 and 1, 2, 1, 3 and 1, 3, and then 2, 3 and 2, 3. Okay, that's what we call shear decoupling. Makes our lives a lot easier. Now, for an orthotropic material, we can actually take it a step further by applying engineering constants to them. So, of course, if we look at the behavior right now, all our constants are C111, C1122. Makes no sense. However, we can apply engineering constants to start giving it some actual material properties. And the first one, as we can see in here, is we have something called the Young's modulus, which I just have as EII, because if we look here, we have E11, E22, as well as E33. And this makes sense because we said that the behavior is different along the three different basis vectors. Now, what is the Young's modulus? Well, it's simply the ratio of uniaxial stress to uniaxial strain in the direction of basis vector EI. Nice and easy. The second one that we can see there, it looks like a V, but it's actually a Greek letter nu, which we have called nu ij, or the Poisson's ratio. So what is this? Well, this is the negative ratio between the axial strain in the direction of EJ to the axial strain in the direction of EI when the material is uniaxially stretched in the direction of EI. Now that's a lot of words. No one likes all those words. However, it's actually pretty easy. You guys have dealt with Poisson's ratio before, so most of you know what it is, but for those who don't, it's basically this. For civil engineering materials, and I want to make it clear, civil engineering materials, because there are cases where this doesn't really hold, but it's basically this. If I were to compress a box, we expect that once I compress that box vertically, it is going to expand horizontally. And this is why I say sometimes, because there are materials that when you compress it, it also compresses in that other direction and vice versa. But for the most part, for civil engineering materials, concrete, steel, if we compress them, they're going to start to expand horizontally. That's basically what the Poisson's ratio takes into account. Finally, we have the shear modulus down there, which is the ratio of shear stress, sigma ij, to the engineering shear strain, gamma ij, in the plane defined by EI and ij. All right, so those are the components, not too bad. And if we look at the matrix, we actually see that we did a little something a little bit sneaky to you guys. So remember before when we were defining these reductions, we had that stress is equal to C times strain, right? We had that C, which is a stiffness matrix. Now if we look, we actually have strain on the left-hand side, and we're taking a matrix and we're multiplying it by stress. Now, I already hinted that once we do this inverse here, the matrix actually has a different name. So in this case, when we take a matrix, multiply it by stress to get strain, this is actually called the compliance matrix. And instead of C, we have it labeled as D. Now, of course, they're related because it's just the inverse. So if I know my stiffness matrix C, I just take the inverse to get D, and vice versa. Now, another thing that we said about the stiffness matrix, which also applies to our compliance matrix here, is that the matrix is symmetric. Therefore, if I had the component 1, 2, it's going to be equal to the component 2, 1. So if we look at component 1, 2, and 2, 1 here, we see that we need different parameters to calculate them. So if we look at 1, 2, we have the Poisson's ratio 2, 1 divided by the Young's modulus 2, 2. However, for the component 2, 1, we have the Poisson's ratio 1, 2 divided by the Young's modulus 1, 1. So different components. However, even though they're different components, it still has to be symmetric. So if I were to calculate the Poisson's ratio 2, 1 divided by 2, 2, well, that must be the same as the Poisson's ratio 1, 2 divided by E, 1, 1. Just a little fun fact to remember. A lot of students start forgetting that the matrix is symmetric. They come to me and they say, Clayton, I don't have what E11 is. I can't calculate that component. And I say, well, you actually can because you already have it from E22, V21 divided by E22, something like that. So it's a little bit sneaky. Now we move on to the next material, which is called the transversely isotropic material. Now, this one gets a little bit more tricky, but it's actually easier. Now, for a transversely isotropic linear elastic material, there exists a plane in which every plane perpendicular to that plane is a plane of symmetry. Well, what exactly does this mean? In essence, the behavior is going to be the same along two of the basis vectors. So not all three, but two of the basis vectors, they're going to behave the same. Common example would be some soil. We know that soil builds up different layers. Therefore, if I were to look at this in the E1 direction, it's going to be the exact same as the E3 direction. So these two planes right here, these would be considered plane of symmetry. If I were to pull in the E1 direction, it should be the exact same as if I were to pull in the E3 direction. However, as we can see due to these cross sections, if I were to pull vertically in the E2 direction, well, that would actually give me a different response. But basically, with these planes of symmetry, we can find something called the axis of isotropy. Isotropy. I always have a really hard time saying that, isotropy. But basically, this means that any plane that can be rotated around this axis is going to be a plane of symmetry, which again makes sense because no matter which direction I pull this horizontally, it's going to be the exact same. However, when I pull it vertically, that's when it starts to change. So because of this, we basically take the exact same relationship we had for an orthotropic material, but now we can actually start making some adjustments to account for the fact that two of these planes are going to behave the same. As we can see, the orthotropic material, we had 9 different constants, but now we simplified it down to 5 constants. And again, just a little trick that you guys always need to remember, that this compliance matrix D here, it's symmetric. So even though it looks like we may not have all the components that we need, we can utilize the symmetry so that we do. All right, so that's transversely isotropic. Now, getting into the one that I said is the most popular by far, you guys have probably all seen it, and that is an isotropic linear elastic material. Now, an isotropic linear elastic material, the response of that material to stress is the same in every direction. It's actually independent of the coordinate system. So it doesn't matter if I pull along E2 or E3 or E1, it's going to have the same response no matter how I pull. Therefore, we can simplify this down into actually two material constants, which we see as nu, the Poisson's ratio, as well as E, the Young's modulus. So of course, the Young's modulus, in this case, since it's a nice isotropic material, we can simplify the definition to the slope of the stress strain curve during a uniaxial tension test. And the Poisson's ratio, nu, is the negative the ratio of the transverse strain to axial strain during a uniaxial tension test. Nice and easy, right? Well, some of you guys may be looking down at the shear components and saying, well, we have a component G, but you said we reduced it to 2 material constants. How the hell do we have a third? Are you forgetting about it? What's going on? Well, if we look at G, which is called the shear modulus, it's actually a function of the Young's modulus as well as the Poisson's ratio. So the shear modulus is the slope of the shear stress versus the engineering shear strain of a linear elastic material. Therefore, I can calculate G as simply E divided by 2 multiplied by 1 plus nu. And we can see that, yeah, it's just a function of both the Young's modulus E and the Poisson's ratio nu. So even though it looks like I have 3 different components in that compliance matrix, I basically have 2 because once I know E and V, or E and nu, sorry, I can calculate G. I have everything I need to know. Now, when we're talking about additional material constants, there's a second one to always kind of be aware of, and that is called the bulk modulus K, where the bulk modulus is the slope of the hydrostatic stress versus the volumetric strain of a linear elastic material. And it can be calculated as simply E divided by 3 multiplied by 1 minus 2 times nu. Great, bulk modulus, who cares? Why do we want the bulk modulus? Well, the bulk modulus is nice as that it indicates how resistant a material is to compression. So if you guys want something very stiff, you guys can look at the bulk modulus, something like that. All right, so these are basically the nice constitutive laws that we know. However, once we get into modeling and stuff like that, we can actually create some nice assumptions or conditions to actually simplify it. So keep in mind that whether we're dealing with an orthotropic, transversely isotropic, or an isotropic material at this point, we still have that 6x6 compliance matrix. However, we can make some simplifications to actually narrow that matrix down from 6x6 down to 3x3. The first one is called the plane stress condition. So this is something I almost guarantee you all have heard of. It's going to be very, very popular once we start talking about beams or if we're talking about the finite element method. But basically what the plane stress condition is, it's a condition that's assumed when all the stresses on a material act on the same plane. Therefore, if all the stresses are on the same plane, let's say the E1, E2 plane, therefore sigma 1,3 is equal to sigma 2,3, which is equal to sigma 3,3, which is actually equal to 0, because again, all those stresses are on the same plane. Why is that nice? Well, our stress tensor actually becomes the following, where we have sigma 1,1, sigma 1,2, and sigma 2,2. So instead of 6 unknown components, we actually only have 3. And this results in a strain tensor of epsilon 1,1, epsilon 1,2, epsilon 2,2, as well as epsilon 3,3. Now, because of the simplification, we can also simplify our compliance matrix, which is now found below. So instead of it being 6x6, we now see that we have a nice relationship between the strains and the stresses by a 3x3 matrix, nice and easy. Now, the one thing that we need to emphasize here, and this is something that undergraduates forget all the time, this new compliance matrix here, this relationship, it doesn't have a way of calculating epsilon 3,3. So notice that even though we have 3 stress components, we actually have 4 strain components. So to calculate E33 or epsilon 3,3, we utilize the assumption that the material in a plane stress condition can expand or contract freely in the E3 direction. Therefore, because of this, we can actually calculate epsilon 3,3 as negative nu divided by E multiplied by sigma 1,1 plus sigma 2,2. So typically what happens in these sort of scenarios is we can calculate what sigma 1,1 is, what sigma 2,2 is, and then we can find out what epsilon 3,3 is. Nice and easy. All right, so this plane stress assumption, again, one of the things that we're assuming also is the material can expand or contract freely in that E3 or the thickness direction. All right. Now, the final thing that we're going to cover is kind of the opposite of plane stress, which is called the plane strain condition. And just like plane stress, this is assumed when all the strains on a material act in the same plane. Therefore, epsilon 1,3 is equal to epsilon 2,3, which is equal to epsilon 3,3, which is going to be equal to 0. This simplifies our strain tensor to the following, where we now only have 3 unknown strain components. Therefore, we can find our simplified stress tensor. And again, just like the plane stress condition, we actually have 4 components that are unknown rather than 3. So we have that sigma 3,3 down there, just something to be aware of. Now, because of these simplifications to our stress tensor and our strain tensor, we can have a new compliance matrix, which went from 6x6 down to 3x3, which we can see we have a nice relationship above. But remember that this new compliance matrix doesn't calculate that 4th component, in this case, sigma 3,3. Therefore, for plane strain condition, we assume that the material is restrained from expanding or contracting in that E3 direction. So plane stress, it's free to expand or contract. Plane strain, it's restrained or restricted from expanding or contracting. And because of this, we can calculate sigma 3,3 as nu, the Poisson's ratio, multiplied by sigma 1,1 plus sigma 2,2. And that's basically it for the constitutive laws. I hope it helped. I hope it shed some light on these. I boxed in all of the important ones. So when you guys are doing your assignments or if you guys are ever doing a test, just look at the ones in the boxes. It's very rare that you really need to know how to derive them. It's more important that you guys need to know how to use them, which is great. The use is very simple. If I have stresses, I can calculate strains, or if I have strains, I can calculate stresses. So that's it for this video. Thank you guys so much for listening. I really appreciate it. I will see you guys in the next lecture video.